substance in which the solute is within. Likewise, the solute is the thing that you can kind of think of as it goes into the solvent. So think of it like, say we have this bowl, right? And this will be our solvent bowl. And this has a bunch of molecules that are kind of arbitrary, and we'll just call them the circles. But we also have another bowl, which is our solute bowl, which has a couple of squares, right? So solvents that you know are things like water. You may be familiar with hexane, but water is known as the universal solvent. Solutes, if you have salt water, you have some, probably some sodium chloride solute. You may have sugar in the form of glucose as your solute. But these lead to, when mixed together, we have our solution, which is a combination of solute and solvent, in which the solute is evenly distributed among the solvent. So, right off the bat, is a couple very important measurements. So, first off, we have the ratio of the two, which is R, which you can think of as squares, which remember are solute, over circles, which are solvent. And in this case, we have 2 solute per 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 solvent, which comes out to 0.2. Or we have the fraction, which is solute per solute plus circle, solute per what essentially amounts to solution. So this is 2 over 2 plus 10, which comes out to 2 over 12, which is 1 over 6, which is 0.16 repeated. So now I got that kind of basics out of the way. Let's go into some more technical, fractional concentrations. So, the first one is the biggest exception of all of them, in terms of it is the one that doesn't involve the solution, and we'll call this one molality. This is, we have the symbol little m for it, and this is the square per circle. But unlike the ratio we just did, this in terms of moles of solute per kilogram of solvent. So in the example before, you think of it as 2 moles of sodium chloride per, and let's go with 5 kilograms of water. Now, that would come out to be 0.4 m. this is squares per square plus circle. And this is in units of moles of solute per liters of solution. So this one, molarity, is a very important unit to remember because it comes up all the time. The reason that it's very important, because it's very easy to measure. You can very easily find the number of moles by taking some, by measuring out how many grams of solute are added and then converting that to moles and then just finding the volume of your solution. And it's a very useful concentration unit to know. Then next we have our weight fraction, and this is similarly to molarity, squares or square plus circle, also known as solute per solution, and this is grams of solute per grams of solution. So this would be something where if you knew the weight of both of them, then similarly if you took this ratio and multiplied it by 100, you get the weight percentage, which gives you the number of grams of the solute per 100 grams of solution. This is very helpful when you're going over empirical formulas, things along those lines. And additionally, we have ppm, which is parts per million, which, like before, is another solute per solution measurement. This one's slightly different because this is all in terms of how many grams of the solute per 1 million grams of solution. So this unit is mostly used when there's trace amounts of the solute within the solution. So people would use parts per million when measuring, things like carbon monoxide, which as many of you guys may know is poisonous. Carbon monoxide in the air in your room, where you'd have something like 1 part per million or something very low like that. You wouldn't use parts per million to measure the amount of nitrogen in your room, because you'd have 700,000 parts per million. That's really not a useful measurement. But additionally, we have our density, and that's the Greek letter rho, which is a weight per volume measurement. Solute per solution, which is grams of solute per milliliters of solution. And as you guys might be able to recognize, I mentioned that you can measure the grams of the solute, convert to moles, and take the volume and have the solution. Density and molarity are pretty closely related. Because calling this density isn't quite correct. It is density, but it's much more of a concentration unit. So for the moment, we'll cross that out. which is moles of solute per moles of solution. This one, it's not used super frequently, mostly used in empirical formulas, but it's still very important to know. But beyond that, we have a couple more. Beyond molality and molarity, we also have one that's called normality. And this is the moles of charge per liters of solution. So, specifically, this is plus or minus charge. And so, if we go back to our example of 2 moles sodium chloride per, let's say, 5 liters of, the solution, which technically wouldn't be H2O, but per 5 milliliters of the salt water, we can then see that given plus or minus, we can just kind of eliminate one of them because they're both a singular charge. We have 2 moles of charge per 5 liters, which comes out to 0.4 normality. But if we were to have something like 2 moles of, let's say, calcium 2 plus, then we'd have 4 moles charge because calcium has a charge of 2. So calcium would have 0.8 normality. And then finally we have osmolarity. We have osmolarity, which is moles of positive and negative charge per liter of solution. So, taking this example from before, 2 moles of sodium chloride per 5 liters of solution. Because we have both the plus and minus charge, this is 2 charge times 2 moles divided by 5. It's going to 0.8 osmolarity. And so if we take our calcium example, if we do some calcium 2 chloride, we end up getting 1.6 osmolarity. So, one last thing I want to go over, and I'll bring it back over to this page for a second. So, one really important equation to remember is that molarity is equal to N, which we'll say is the number of moles of the solute per V for volume of the solution. This is very important because it gets us to the equation of Vm equals N. Now this is volume times molarity equals the number of moles of solute. And this, when we get to dilution,